This is a video for Stats, Chapter 12, Section 2, chi-squared test. This is the symbol for chi-squared. This tests if there's a relationship between variables. Section 1, we looked at whether there was a difference between proportions. This is checking for a relationship in a two-way table between two types of variables. It uses expected counts, which we learned back in Chapter 5. To review quickly, expected counts state what counts we expect if there is no relationship. So what would I expect to see come out of a study if there is no relationship? And if our counts are very different from the expected counts, then we have evidence that there is a relationship. These are like the center or the standard that we compare our sample counts to. One other quick note, in a 2 by 2 two-way table, chi-squared is the same as z-squared, and so your chi-squared test results will match the two proportion test results from section 1. Okay, a few formulas here, and I'll hold it up so you see the whole page in case you want to copy these notes down. You can pause it and do so now. The formulas for the expected counts, we find those by taking the column total times the row total divided by total. And that is a repeat from something we learned back in Chapter 5. And we'll demonstrate it later. Chi-squared uses something called components. Each box will have a component. I calculate the components by taking the observed counts minus the expected counts, squaring that value, and then dividing by the expected count. We do this components for each box. Chi-squared then as a test statistic is found by taking the summation of the components, or the sum of each of those calculated from each box, and we'll demonstrate that later. These formulas are also in the book if you want to go into there to get the formulas in Chapter 12, Section 2. Next is the degrees of freedom formula. Degrees of freedom does r minus 1 times c minus 1. So I'm going to take the number of rows minus 1, the number of columns in the two-way table, minus 1, and multiply those two values together. And it does not take into account the total row and the total column, just the data values. The distribution for chi-squared has three components. First, the shape is a non-negative right-tailed, just like F distribution. And it ends up looking usually something like this. Very similar to what we saw with F. The center is the degrees of freedom. So whatever the degrees of freedom is the center of your distribution. The spread, it changes depending on the size of the two-way table. A 2 by 2 would span from 0 to about 4 or 5. The cutoff or borderline score for a 2 by 2 is 3.84. A 2 by 2 table would have a degrees of freedom of 1. And that would produce that borderline result of a p-value of 0.05. So this is the cutoff. If you're bigger than this in a two-way table for a chi-squared score, then that's unusual, and we're probably going to reject because the p-value is going to be small. If you're smaller than this, then it's not large, and then the p-value would not be small. In a 3 by 3, that would span all the way from 0 to 10 or 11. The cutoff score that produces a borderline result is about 9.5. The degrees of freedom for this would be 4. And again, the degrees of freedom takes how many rows there are minus 1, which would be 2, times how many columns there are minus 1. So in a 3 by 3, that would be 2 times 2, or 4. Next, we're going to take a look at the chi-square test. We test for a hypothesis that there is no relationship as the null. If we have the alternative, then we're saying that there is a relationship. The conditions for a 2 by 2, all expected counts must be at least 5. This is also true for larger tables, but the larger it gets, the less strict this requirement becomes. And again, one difference here in the two proportion test we did, we needed at least 5 in the observed counts, like the actual data that we gathered. Here we're looking at it in terms of the expected counts being at least 5. not the observed. Test statistic is your chi-squared. It's the sum of the components that we talked about earlier. Degrees of freedom, there's your formula again. The p-value. Now we're going to use the prism to do this, to find the exact p-value. We're going to go F5 distribution, F3 chi-squared, F2 CCD, and then you're going to put your chi-squared number in as the lower, infinity, 999 is the upper, and then the degrees of freedom. Now if you have a 2 by 2 or a 3 by 3, you know those cutoff scores. Since you know those cutoff scores, we can go ahead and just make conclusions based off of that. So if I had a 3 by 3 and my chi-squared was 12, that's bigger than the cutoff. So that means we're farther out, which means the p-value would be smaller. So you can use those cutoffs to make a conclusion, but to get the exact p-value, you have to do this, and we will demonstrate that. The conclusion: if this score is large, p is small. You have evidence of a relationship. If chi-squared is not large, lower than these cutoffs, or something not very large, then p is not small, and there's no evidence of a relationship. Which should make sense, because if we're comparing in the chi-squared, we call it back to our formula, the components, how far away the observed are from the expected. Observed minus expected. If the observed and the expected are not very different, then these numbers would all be low. All the components would be small, therefore the sum of the components, chi-squared, would also be very small. So observed and expected very close to each other. Expected says there's no relationship. If the observed are close to that, then my observed have no relationship. And if these are close, these numbers are going to be small, and chi-squared will be small. So the smaller chi-squared is, if it's not large, you don't have evidence of a relationship. Let's go through one example. I'm talking about migraine medicine. We have a drug group and a placebo group. Did their migraine symptoms improve or not improve? Out of 50, 12 improved with the drug. Out of 75, 10 improved with a placebo. So I see here's my 4 values that I'm focused on. We're going to start by just running some calculations. The expected counts. The expected counts. Take these subtotals. 50 times 22 divided by the total of 125. So I expect 8.8 here. Do the same thing for each box. 50 times 103 divided by 125. 41.2. I'm going to do the same thing for both of those. I'll pause a moment so you can look at the calculations. The components are calculated by doing the observed minus expected, squaring that value, and dividing by the expected. So for the first box, my observed, 12 were observed, I expect 8.8. 12 minus 8.8, square that, and divide by 8.8. That's my component. Do the same thing for the other 4. Observed a 38, expected 41.2, 38 minus the 41.2 squared divided by 41.2. Pause a moment so you can take a look at those calculations. So these 4 are the components. Chi-squared is calculated by adding those 4 components together, and I get this chi-squared value. So here's the test. I have a alternative of no relationship, a null of no relationship. Alternative is a relationship. Conditions. Expected are at least 5. And I look at the expected, yeah, all of these are at least 5. The chi-squared is 2.36. The degrees of freedom, well, it's a 2 by 2. So there's 2 rows and 2 columns. 2 minus 1 times 2 minus 1. 1 times 1, degrees of freedom is 1 for a 2 by 2 table. The cutoff for a 2 by 2 is 3.84. So I know that 2.36 is not bigger than 3.84. It's not large, which means the p-value is not going to be small. Let's find the exact p-value on the calculator. So I'm going to look at, on the calculator, distribution, F3 chi, F2 CCD, and I'm going to put in my chi-squared, 2.36. Upper is always infinity. Degrees of freedom was 1. And when I type that in, I get a p-value of 0.1245. So my p-value about 12.5%. It clearly shows that there is no evidence of a relationship between the drug and improving symptoms. So, between these two variables, the drug and improving symptoms, I have no evidence of a relationship because there's a p-value as high as 12.5. That concludes the lesson. Make sure you complete the practice problem that is posted.